The University of Huddersfield, inspiring tomorrow's professionals.
Trevor, this is Josiah. We have a third co-author on this presentation, Jeff, but he had to stay in Colorado. He got sick right before his time to come across the ocean. Josiah and I have been at Harvard for many years working on this project together, although it started significantly before we got there. And the point of Abjad is to make scores. We are conventional composers writing for musicians, and so this is about modeling parts of the creativity that go into making documents that ultimately get handed out to the players. So in that spirit, we have some of our own scores that we brought, just for you to page through while we're talking. So I'll just pass these out. And all of these are example output from Abjad, example output from the system. Here's a lovely one of Josiah's scores that's loosely leaf, so just kind of all right, great. So the structure of the talk or the workshop will be very much like what Torsten just presented. We'll motivate the whole thing by just demoing up front to show the construction of some time structures, right, and how that works. Then after that, we'll back up and talk a little bit about the history of the project and how it is that we came to writing music in this way. Then we'll actually show a little bit of the music so you can hear what the results of working this would sound like. A couple of excerpts. And if we had, depending on time, we will look at two other projects that have hooked into Abjad and are using it as a type of API for other types of work, which can be fun to look at. And then we'll wrap up and take time for questions. So let's start. So we have this type of blurb on the website and all of the artifacts that we always put out about the project. I will read to you. The Abjad API for formalized score control extends the Python programming language with an open source, object-oriented model of common practice music notation that enables composers to build scores through the aggregation of elemental notation objects. Not exactly a real kind of punchy tagline, but in some respects, the kind of 45 minutes that we'll spend in this workshop is an unpacking of that statement. And in fact, the kind of conclusion slide just reiterates this. And hopefully after we go through these examples, this will make more sense, at least in intuition. All right, let's just demo. Let's just make some classes and write some code. And we will shift into a terminal window, open up the I, and type some stuff. So I have the same source that Josiah is using here, so we can talk about things together. So if you start Python, which is on your Mac, and ask for the global namespace, you'll see that there's not much there. This is by design. Python keeps a very clean global namespace, so the user-defined symbols are all that you see. Python doesn't know very much about music. The 55,000 or so packages that are available on the internet, also through the Python package index, extend Python for all sorts of applications. The mathematicians are moving to Python in droves due to the availability of the NumPy package. Aerospace engineers use Python. Google uses Python to manage its infinite server array. Many, many different organizations and teams use Python. There hasn't been much in the way of music notation, however, and Abjad fills this gap in a massive way. So Abjad is a Python package like all of the others. We've architected it exactly like the major Python packages that are on the internet. If you import the total contents of the package with some syntax that looks like this, and then you look at the global namespace of Python again, now Python knows rather a lot about music notation. So the class names that are listed first are the basic elements of score that you're likely to use all the time, so we just import them for you. And then the remaining stuff kind of at the bottom there and smashed together lowercase, those are full packages that then extend Abjad for specialized purposes. For today's talk, what we'll do is we'll look at the Rhythm Maker Tools package, snappily named because there are classes in there to make rhythms. So we want to start with just making some rhythms. Just get out there. Okay. So in the simplest case, let's just make a single voice of notes so that we see how duration mapping can work. By the way, not all composers working with Abjad use this package. We both use this package a lot, and the scores that you're kind of passing around. The rhythmic surfaces of those things are generated using the code that we're showing here. But this is kind of like a mid-level sort of application of the system. I think when composers first come to the system, they spend a lot of time making notes by hand, making chords by hand, figuring out what pitch syntax looks like for obvious reasons, because you need to know what those conventions are. But just to keep things interesting, we're going to jump to kind of the meso level with this example. So if you want to make a node rhythm maker there, it's just class instantiation that works the same in every language. And the node rhythm maker by itself doesn't do anything. It requires duration input. Lots of ways of expressing durations, but the most straightforward is probably just time divisions, which are not fractions but pairs. They can be treated like raw durations, like meters, like trees. In this case, we'll pass a list of four or so divisions to the node rhythm maker, and it will go make notes that correspond to this. So let's take a look at the call syntax. The durations, everything American duration terminology, of course, British names are crazy. 3/8 notes, or 3/8 of a whole note, 5/4 of a whole note, a quarter note itself, and 13/16 of a whole note. So some of those durations, of course, are going to need ties or something to express them because they're not native to the binary system of Western notation. What comes back will be a list of selections of notes. Let's see what that is. Great. And so we can see, we're about to look at notation, which will clear this up, but just from the interpreter representation here inside Python, you can see that we don't get 4 notes get back, we get 4 selections of notes, so that things that need ties can be tied, and so on. Okay, so to view things, we enclose selections of music inside something like sap, or voice or score, sap, and then we just call show. And what's happening here is that Python is opening a subshell, formatting everything that we just made as Lilypond input, which is a text-based notation system that you probably know about, maybe have used. Opens a subshell behind the scenes, passes that input as a large string to Lilypond. The output from Lilypond is a PDF, paint, something like that, in this case PDF. And then we push the PDF so that we can see what it is that we've been working on. So there, fine. Now, since what we're going to do is just model rhythm to the exception of pitch, we can do a little bit of typographic customization here. Abjad affords a large amount of typographic customization because Lilypond gives us a large amount of typographic customization. But for these examples, what we'll do is null out. Yeah, okay. So we've Iron Chefed up some materials ahead of time. So from our presentation directory, we will import a function that nullifies pitch and meter so that we can just look at the rhythmic durations that we'll get increasingly complex. And it is the function makeSketch that was just imported from our presentation below. So now the sketch comes back and is formatted such that durations, first of all, take up the amount of time, there's proportional spacing going on, so that when we start to introduce tuplets, it's easier to visually see what's going on with timing. Got the rhythm meter. Lilypond is very good about not enforcing people to work in the context of measures, right, which was one of the primary problems with Finale and Sibelius throughout their entire history. So this is nice, we're modeling time. All right, let's see this work again, right? Let's just pass more information to our node rhythm maker before we do something non-trivial. Let's make a new list of divisions. 4 or 5 of them again. Some will need ties, some will notate natively in Western notation. Let's pass that new list of divisions in so that we get comfortable with this define, interpret, view, define, interpret, view loop that makes up the user experience of working with Python extended this way. All right, you have more questions? Okay. First takeaway point about working in Abjad is that working in Abjad means working in Python. You are not working in a custom programming language, right? You're not learning new syntax, not really. You might learn some new patterns because our classes have patterns associated with them that we have tried to take from all over computer science. But you're not learning new syntax to work with those patterns. So, for example, in-place multiplication, which just multiplies out the number of references inside some container in Python, regardless of the container, as long as it's separable. Looks like this. So now instead of 5 divisions, we have 100 divisions. Pass that back in and view it in that. Not exactly the most interesting music, but you know, debugging the wallpaper. So essentially what we've created here with 4 or 5 lines of code is a way of visualizing stuff as durations, right? So we want the literature on computer-assisted composition is full of random-based examples as a way of getting input. Neither of us work with random values in our music, but why not? The way that we would do that inside of Abjad, which means inside of Python, is we'll import Python's random module. We didn't code any of this, right? This is in the Python standard library. It gives you 10 or 12 basic functions to generate things according to Gaussian and binomial Poisson distribution, all of which are in our history of the last 60 years of computer music, of course. And we can use the basic syntax of Python. Here we're showing list comprehension, which is a one-line form of a loop, which is special to Python and idiomatic Python programmers, to generate numerators for time divisions. Each numerator will have a value between 1 and 16, and then we'll interpret that as a number of 30-second notes. So we use a second list comprehension to make the time divisions expressed as numbers of 30-second notes that they are. And there are 100 of them. They're largely different from one another according to uniform distribution. Visualize as a sketch. Show the sketch. Still looks like wallpaper. Nicer wallpaper, but nicer wallpaper. Okay. And you can see the tagline at the bottom, right? We're leaving the stuff that says Lily Pond is what's behind this doing the rendering. So pause. Why are we using Lily Pond? We have a history slide we'll get to in a minute where we show the other things that we tried to use before. And again, we're using Lily Pond because it's open source and we're not going to work with anything that's not, period. We're also using it because the input to Lily Pond is text-based, right? Normal humans sitting around kind of typing things in. There are a couple of editors on the internet that work fairly well as well. But we're not having to go through the process of making a binary input file, right? This is the stuff that goes into Lily Pond is not like a vanilla Linux file, right? It's not like a civ file. Humans are writing these files, and so we can get them to be machine generated as well. So the clear text input to Lily Pond and the fact that it's open source are the primary drivers of this decision. And the more knowledge that our users have about tweaking Lily Pond files, the more they can tweak the stuff that they make inside of Abjad as well. All right, let's up the complexity just a little bit. So one of the classes available inside the Rhythm Maker tools package is something called Italia Rhythm Maker. So we're taking the term from 13th century usage, not really meant to be neo-medieval, but Italia, you will remember, was just a repeating pattern of something, a cycle in medieval usage. Usually durations, actually, although it could be pitches. So we have an object-oriented model of lots of stuff in the system. We're trying to just use loop practices that go back to the 90s for the majority of the work in composition. So here we can define Italia, and that just says, how about we have an infinitely repeating pattern of durations that will start with 1/16th note, 2/16th notes, 3/16th notes, and then move back around. We initialize the class like that. And the interface to the class is such that as you ask for yet more stuff, arbitrarily, probably you just get this cycle coming back. So this is an infinite input generator. Here we ask for 20 different events. 20 different events come back, but they're all patterned 1, 2, 3, 16 notes, 1, 2, 3, 16 notes. All right, so you can use Italia to do a couple of things. We have Italia Rhythm Maker, which accepts one of these Italia objects as input at configuration time. And then makes rhythms like our very simple note Rhythm Maker with a little bit more interest. So there's our initial, those are the ones from the beginning, right? Yeah. Same 4 divisions that we used at the beginning. So we can pass those 4 time divisions to our new Italia Rhythm Maker, wrap the input, wrap the output in a sketch, and show the sketch. Okay, so what's going on there is that we're using beams to clarify things. Same amount of time, right? So the 4 different beamed figures correspond to the 4 input divisions, which are equal to 3/8 notes, 5/4 notes, which is longer, 1/4 note, which is shorter, 13/16 notes at the end. Those are the durations of the beamed figures. And then the patterning of attack points inside of that is given by the Italia of 1, 2, 3/16 notes, 1, 2, 3/16 notes, 1, 2, 3/16 notes all the way across. And to preserve those rhythmic relations, if we cross the boundary between 2 rhythmic figures, we insert a time, and the duration math is taken care of. This doesn't sound like anything except because you're not hearing beams yet until we add accents or phrases or whatever. sounds like a repeating tally of 3 notes, but we're setting up the possibility of working with 2 or 3 divisional structures. Okay. How do we do that? Well, we have other object-oriented specifiers that you instantiate and then pass to the rhythm maker that you're working with. So Talia Rhythm Maker, you go to the API, which is available online, or you go to PDF. And you look at Talia Rhythm Maker and see, oh, you can do things to specify the way that ties will work in patterned or algorithmic ways, for example. You can also specify the way that tupleting will work, according to a couple of different ways. We'll show one. You can specify the way that the end treatments, the beginnings and ends, the beginnings and endings of individual chunks of output are treated, say by turning things into rests, and so on and so on and so on. These come from our own compositional practice, from the practice of people who are on the Abjad list, literature examples, and wherever. So let's see. Here Josiah is coding up some stuff. So first we'll make a tie specifier that says, these different chunks of output, why don't we tie between each of them? So we're effectively holding across each of our rhythm figures. You can pass in arbitrary patterns to that if you want to. Then extra counts per division is a way of causing time manipulation, basic tupleting to happen. The pattern 0, 1, 1 that's assigned as an argument to that will be interpreted such that our first rhythmic figure is not time scaled at all. But then our second and third rhythmic figures, cyclically, will have one extra element, one extra count shoved inside. Figures, second and third figures will be ever so slightly faster than the governing meter. And then we'll repeat that so that the fourth figure is untreated, fifth and sixth figures are treated, and so on and so on. Anything else? No. Pass. Oh, and then a burnish specifier, which is one type of colorfully named object-oriented representation for a pattern that says, look, how about the first figure will be have its starting value rested. The second figure will be left alone. The next figure will have its starting value rested. The next figure will be left alone. So in alternation, we'll create some rests. We could initialize a brand new Talia Rhythm Maker with these things, or we can use the templating function, new, which takes an existing object and adds some extra configuration to it. Great. So now we have a slightly more exotic Talia Rhythm Maker. We'll pass in the same 4 divisions just so that we can compare it to the previous. Okay, so still 4 cells of output that correspond to the 4 time divisions that were passed as input. And now you can start to see that the second and third figures cyclically an extra element put in. Ties are across all figures, except that we then go back and on every other figure make rests, which will block some of the ties. Underneath that, or together convolved with these settings, is still the Talia of 1, 2, 3, 6, 7. Yes, you can make rhythms that look a little bit different, but the idea is that you would be working with these classes in their output iteratively, as we're showing here, quietly yourself, to get closer and closer heuristically to rhythmic surfaces that would actually be useful for your own course. All right, so let's finish this demo by making a score with some, yeah, let's score. Yep, let's do it. So all the flow control constructs in Python, as probably a lot of you in this room know, are one of the really attractive things about working with the language because they're extremely straightforward. Python's flow control, the loops that are available, it just looks like pseudocode. It looks like procedural pseudocode. Which if you spend a lot of time in functional programming can seem to be not very rich. But if you're teaching programming to newcomers, which many young composers are, it can be extremely helpful because the pseudocode graphs that they're likely to have seen match very closely the code that they'll type when working in Python. So here what we're going to do is create an empty Abjad score. And then just use a Python loop to go through 12 times a suite of 6 lines of code. And what happens when we go through that suite is that we will first make some music in the way that we've been doing it, with the rhythm maker that we've defined. We will wrap the output from that voice, wrap that voice into a staff, append the staff to a score, And then before exiting the loop, we'll just rotate the input that we have so that things start to spiral around. We make successive voices of rhythmic output. When that's done, we have a score that we can wrap inside a object-oriented representation of a LilyPond file. There it is. The file has chunks in it. One of them is a score chunk. The score has 12 staves. Each staff has a voice. We'll show the whole thing. Okay. So the idea is not that this is a percussion piece for 12 wood blocks, although maybe. The idea is that this is a virtualization of part of the pre-compositional process. I'm not really sure that I believe in pre-composition. I think that in the best cases, pre-composition is kind of marbled inside of the work of legit composition. But in any of those moments in one's process where you are thinking about the materials separate from their exact musical context and aware of the relationships inherent in the material before it's placed in its musical context, this can be a very powerful way of working out your own thoughts about the material that you work with. When I make matrices of rhythms like this, I'm usually not then taking a Brownian walk through the cells. I'm usually looking at this as though it's real, potentially real musical material, taking my metaphorical knife and then lifting from these sorts of materials and inserting it into whatever real piece of music. Okay, that's it, right? All right, so much for some initial demoing. Just to be clear, all of the pitch things and rhythmic things and harmonic things you could expect are available in the API. We wanted to go in at the middle level so that we could demonstrate using iteration, looping, interrogation, rather than just making basic objects like this. Okay, so some background about the project. Stephen, how are we doing on time? You're perfect. Okay, great. All right, so we've been doing this for a while. Probably like a lot of these projects, it started out as our individual rhythmic composition environments that then grew and grew and grew. So when I was an undergrad at Texas, I started doing this with MIDI files, like probably a lot of people, ran into all of the limitations that MIDI has as a flat file format with timing offsets, express nesting, harmonicity, and all of these things. Later moved to Mathematica, not for reasons of fanciness, but for reasons of wanting a functional programming language. Right? Lisp would have been an equally good choice, but student licenses to Mathematica are cheap. Right? So we spent time working on a system that would maybe be based on expressions and their transformations. And that idea is still actually deeply embedded in what Abjad became. The reason we backed away from Finale and C is because it wasn't workable for what we use, not a rich enough representation of our music here. The reason we backed away from Mathematica is because it becomes extremely difficult to debug and extend Mathematica-based projects as they get bigger. I mean, every physicist who's ever been Nobel Prize winning left-brainer for the last 15 years is on the Mathematica subscription list. But when you look at the way that mathematicians and physicists work inside Mathematica, it's usually not to architect out entire software systems. Right? We should have known this at the beginning, but we went down that path for a while and then left it because there's no testing practices, for example. There are no established best practices, as far as I know, for how automated regression battery should work in Mathematica. We cannot architect out something that's not very good. That's the case. So we left. Then LilyPond came in early. LilyPond's been around since the 90s. The original inventors were Dutch. Spent about 10 years getting the system to a point where we felt that we could use it. We knew about it in the early 2000s, but thought that LilyPond was not sufficient for what we needed. But by 2003, 2004, it was. And so that's been with us ever since. When we left Mathematica, we went to Python. One of our initial collaborators was the Mexican composer Victor Don. He was working on his master's degree at MIT. MIT is very much a Python-based shop, so it was an easy decision for us to switch to that language. We went through the process of writing to Adobe Illustrator files programmatically, which a number of composers, very good composers working right now have done, but felt like killing ourselves when doing that, mostly because there are not semantic footholds for music notation in Adobe Illustrator. Why would there be? Right? So the idea of being able to control semantically grouped things, for example, the accidental sitting, the array of accidental sitting in front of a note that's recorded, it's not there. There's no way to get that aggregation easily. You have to engineer it yourself. So. All right, then on and on and on. Josiah tried using MaxMSP through Access for a while.
I showed up in 2008. So
Yeah.
I didn't know about that yet.
Yeah, so tried to give it a data management focus for a while, but eventually settled into what you just saw demo, which is Python with LilyCon for the output. The first public release that wasn't just our friends was in 2008 on Google Code. We moved it to GitHub later. The current version is 2.16. So there it is, kind of the reasons for why we wound up with the combination of Python. So the idea is that Python is the governing thing in the stack. You're not working with something at a higher level than Python. You're working in Python, into which you have imported Abjad, and underneath of which you are not working anymore with a score, I mentioned on the previous page. We wrote to Lou and Smith's score package for a while because the input is clear text. So that was possible, but it was very difficult to work with because the representation is all numeric, it's Fortran. So that's not there. Underneath this is LilyCon right now. As Daniel Sprigbury's team works at Steinberg, the old LilyCon, or the old Sibelius development team got bought, that's probably most of you know, by Steinberg, people at Cubase. And they're currently sitting at Steinberg making what they hope will be the successor graphic user interface notation package to Formalized and Sibelius. Depending on the availability of the text input interface to that package, we have architected Abjad in such a way that we can output to any comparable text input facing notation system. So we are waiting to see what the output of that one will look like. Just like many people in the community are waiting to see what the output of that package will be like in other respects. And in fact, the architecture all the way down through the formatting engine is designed to be modular. And we've done this for a while. We have not coupled the system tightly to LilyCon. We are waiting for other notation packages to offer up a comparable text-based, open source, public domain interface that lets us extend the system. But right now, we're limited to it. So we'll see what happens in the future. Okay, so some things about the object model. When you start working with this becomes clear if you read through the documentation, but just to whet your appetite while we're gathered here today. Python doesn't enforce an object-oriented way of working. Python is polyparadigm doing that. So there's functional constructs, procedural constructs, object-oriented constructs, and they're all just kind of there for you to decide what to do. Abjad is largely encouraging an object-oriented way of thinking about notation, about composition, and about the simulation of these things. That being said, you're free to work with the system according to any of the syntax that Python gives you. You'll find that at the heart of the thing, there is a tree-based model. Voices do fit inside staves, which can fit inside staff groups, which fit inside scores, we showed in the example. Measures are not really very important because we think that modeling measures as a de facto type of containment is wrong, though you can do that if you want. We take the graph theoretic idea of a leaf and say nodes towards rest, those are all leaves. We do not set up a relationship between nodes and chords that's one containment or aggregation. Instead, we model node heads explicitly. So node is just a thing that contains a node head, 0 to many node heads. All right, and then there's something else too that you'll start to see that might be attractive to people in this room. The relationships, the syntactic relationships that obtain between elements in musical score, we object model those relationships as well as object modeling the items themselves. So you can do things like look at where in a score a chord is sitting. Oh, it's inside a tuplet, which is nested inside another tuplet, which is inside straddling a measure, which is inside a voice that's against another simultaneous voice. You can inspect those sorts of things using the tools that we've given you, and what comes back is an instance of the parentage, so-called, of that relationship, so that you can actually interrogate as objects the structural relationships of things inside the score. This is not present in any of the scripting languages available for notation elsewhere. And these sorts of features are not things that the newcomers to the system largely use, but we have exposed them and made them part of the public interface so that people who are both composers and developers can use those as handles to do structural things with the interface that we built. All the primitive objects are there and work as value objects, comparable to integers, but they're actually classes. And then large groups of functionality have been put into what we call top-level functions or top-level tools, so that, for example, all of the mutators to the score, so we provide a way of splitting things along durations the way that you can in music. All of the mutators are grouped under the mutation interface. And you say any construct that you're working with passes an argument to the mutate function, and then just use the interface of functions available on the mutation features. And those are the basic patterns of working with the entire thing. The system is quite large. It's using 5 collections of pattern. We go to this slide. We have one other thing that we made an illustration on the website for. So the tree-like looking things, so the white and black things, or the color. The white and black things that express the tree, that's what you think it is. That's the nesting of states and containers and so on. Similar to the document object model. The colored stuff, the spanners, are our implementation of things like piano pedal marks, wavy trill spanners, slurs, all of those sorts of typographic things in SCORE that are frequently problematic to model if you are using a duration-based tree for your primary object model. Because those typographic things, one thing they all share in common is that they can cross over whatever hierarchies you're looking at inside your SCORE. Right? There's no problem with a phrase marking going across a measure boundary. There's no problem with piano pedal things subtending a group of ferociously complex nested tuples. There's no problem with the trill spanner going across a bunch of complex rhythms as well. So our solution to this, which is unique, is to object model those things as first-class elements of the system, just like measures and notes and chords and all the rest of it, that are then applied, as it were, metaphorically, to the side of the strictly nested tree. What this means is that in the implementation of the system, we have to do some very clever things when you cut and paste from large structures. But from a user perspective, it means that things like trills are first-class objects that you can iterate the score. So you can do things like iterate the score in whatever temporal order you'd like. Depth first, breadth first, whatever, it's all there. And grab the trills as you go. And they're actual objects that are connected to the things that they govern. So you can do things like algorithmically use the last note of every trilled expression in your score and change the duration of the articulations of those things based on those parameters. So the point is that the colored spanners implemented in the system give you algorithmic footholds for manipulation that are not available in another way of modeling score. It becomes intuitively clear when you start looking at the system. Next, okay, so just some stats. Since the public code base has been, since we have the code base on the public internet since 2008, we've made a lot of, we've extended the system many times. The 500 or so classes that are in there are what you interact with. And it's mostly the methods implemented in those classes that do what you need to do, as we're showing today. There's still some procedural functions, which is the next category of things. The code base is not large. It's less than, we reached a point in the software maturation cycle where the code would get bigger and bigger and bigger for many years. And for the last 3 years, the total number of lines in the system has been increasing, which is a good sign. And this is maybe one of the most important points that I've been trying to make at talks over the last couple of years. We backed away from Mathematica and a couple of other decisions in our technology stack for reasons of maintainability and extensibility. All of the clever optimization of algorithmic techniques in the world will die if there's not a way to extend the system. And by far and away, the experience for 10 years or more doing this is that extension is given, the ability to extend is given by the presence of tests. More important than the decision that this be an object-oriented interface to SCORE is that there be an automated progression driver so that people can actually make changes to the system and see if they're breaking their own code. So we have something close to 20,000 tests, all of which are automated. Those were not built in a year. Those were the collection of almost 10 years worth of active tests. It means that we're able to refactor the system and issue new versions about 2 times a year. It's 100% open source and you can use it in Python. All right, let's actually play. So we have a teaser concert for you. We have here a small concert. So we've just mashed up like 1-minute excerpts from the pieces that we've written in the last 18 months or so. Both of us forward at Harvard. So 3 of these, the first 2, so Josiah me. The first 2 pieces are small, medium ensemble, excerpts from medium ensemble pieces. Then the viola duet that comes near the end, you'll hear, as distinct in its texture, and then we'll close with a little bit of ensemble music. And I think what we'll do is just play the excerpts. It's about 4.5 minutes of music. for that musical intelligence. The point here is that we want this sort of algorithmic and formalized work and the creativity and its simulation that drives it tied back into the production of music. Like we're interested in this being the final destination of this thinking. It's not the pre-compositional interludes and the materials that we visit along the way to get there. It is actually music. And we're grateful also to the players for these pieces. The first two pieces were played by Ensemble Del Niente, an incredible music ensemble in Chicago, in the United States. Elizabeth Moiser and John Pickford Richards commissioned the viola duet, and the last piece was played by Ensemble Mosaic in Berlin. All right, so as we just scroll through these pages, we're up to a very large number of scores that we and our closest collaborators have written top to bottom in Abjad. The music that you just heard, 100% top to bottom, modeled in all of its aspects, rendered, the final PDF, the whole thing, everything wrapped inside the documents, all 100%. We're also, same with Jeff, we're also relatively committed to doing this in an open source and publicly visible way. So the way that we like to work with the system is a GitHub repository per score. So if you would like, you may go get the full PDFs to all of these scores. It'd be nice to make money off of printed music at some point, but it doesn't seem realistic. So you may see both, you may go download from the GitHub repository both the complete scores as well as all of the source code, right, to create these things, beginning to end. All right, so as we look forward in the project, there's some Jeff stuff. Let's look at the usage map. We have a user base now. Since we've both been finishing grad school, getting done with the work of the PhD, we've had to deprioritize some things. And what we've chosen to deprioritize has been kind of user evangelism. We have not spent, there's a job mailing list, it's moderately trafficked, depending on who's working on what. But we have not spent a whole bunch of time seeking out new users, finding out the profile of who's using the system. Google Analytics gives us some clues. We won't bore you with the statistics, but on average, the bounce rate to the site is 60%, which means that mostly people hit the site and then use it. Average amount of time that our users spend on the site is about 3 minutes and 57 seconds, and they're reading the technical documentation and going to pages of the API to figure out how to do things. It's lovely. It's like Christmas to wake up and get an email from a composer in Sao Paulo that says, "Look what I made with your stuff," which happens to us on a pretty regular basis. Those are the kind of locations from which we will links the most for our users. Okay, next. So, wow, okay, so that's great. We're just going to skip the companion projects. Let's go to the conclusion slide, which is the same as the introduction slide. And let me read to you one more time. The Abjad API for formalized score control extends Python programming language with an open source, object-oriented model of common practice music notation that hopefully enables composers to build up scores through the aggregation of elemental notation objects. This is what we hope to get across in a couple of different ways in this presentation. Showing how you can build up rhythms iteratively using the basics of programming in a particularly special way that then results in real music. Thank you for hosting this morning.
Thank you both for a very elegant discussion of the integration of creativity and technology, and also a very passionate defense of open source philosophy. We have some questions, perhaps a couple of questions, and we can perhaps carry on the discussion over lunch.
The question is my favorite. Well, how does interacting with Abjad change the way you guys compose?
It's changed it in dramatic ways. I mean, it's not been a subtle or small thing. I mean, the thing, in a room like this, you usually don't have to make the case about why you've stuck computers into the middle of composing music. In other rooms we do, and it's, I've been doing this for a very long time, and it's very difficult, I find. I mean, if you guys disagree, please say something over lunch. It's very difficult to articulate the fundamental value proposition about why people would do this crazy thing of sticking computers into this highly creative, extremely nonlinear process, which composition is. I would say that to actually answer the question, this has changed my thinking about what music, this is personal, about what I want my music to be. From texture to drama. Right? As one of the things about working algorithmically or formalistically in music is that it seems to result in boxes of stuff. It seems to result in swaths of texture. Right? Our demonstration of working out these rhythms generates, that's why I used jokingly, not jokingly, the idea of wallpaper when we're generating these things. And that doesn't seem to be unique to us or to Abjad. It seems that working algorithmically, it generates swaths of stuff. Arguably listening to the jazz opener to this morning's, it's beautiful moments, right? But conceptually still one box of material, right, of extensible length, which makes it magic. We run into those same sorts of things, and as more and more of the compositional process, as I've been able to encapsulate more and more of it with ideas from computer science, basic classes, basic interfaces, basic modularization, that's given me better control over the boxes and swaths of material, and I've been able to come back around to having things happen. Being able to think about the Matergy sequence of the explosions or the inverse of explosions that I want to have happen to people while they're sitting in a hall, and actually get that to happen. And that was a process of many years. I think I'm still far short of it, but at least it's come back around. And it's because of the availability of basic constructs of computer science. If you want to talk over much. Okay.
This is brilliant work, and I'm very excited about it. And I want to go and download it and start using it. The question is, how long will it take for me to learn it? It's fantastic stuff. It's very exciting. So are you thinking about ways to introduce? But I probably will get through that quickly because I know some programming and so on. But I'm thinking about a composer who is very excited about this. He's for these Sibelius and Finale. There's no way to notate the stuff they want to do. So how do we go about it?
The thing we've learned over years of showing this to people is you can't really get around the fact that you have to learn programming. That's just, you have to learn how to program. And Python is easy. I learned Python, I was introduced to Python, and then because I wanted to work on Abjad when I first met Trevor, and I would say that I was getting musical results within about 2 months of learning the language from scratch. Python is very easy.
Josiah's also an excellent developer, right? An architectural oriented, and not just giving worked with a lot of developers over the years. So this is why I'm interested when Torsten talks about what it's like teaching constraint programming to undergrads. It really depends, right? I've had the chance to teach a number of workshops and classes on this, and there are even a couple of university programs that use Abjad in the US as a foundation for some of the computer system classes. And the results vary, mileage varies a lot, because part of what we believe, as I pointed to, we want composers to become programmers, which is this kind of poisonous proposition, but that is what we believe. We think that in general composers make very good programmers, for the most part. There is a type of structural thinking that is in common to both practices. It's hard to articulate. Details of that, our cognitive colleagues do a better job of it, but we know that it's there. So what we hope to do is to meet undergraduates, especially, kind of where they are, and teach formalistic thinking about music and programming at the same time in parallel. We think that that's the right pedagogical approach. Now, for our peers and colleagues and other researchers, it depends on your own background and what programming languages you have.
Documented all the functions and everything. Yeah, cool.
The API is about 900 pages. If you, well, the PDF is given. We violate the best practice and include the PDF in the package.
Right.
So you'll get it if you.
With that, we should curtail the debate. I think we should break for lunch and carry on the discussion even formally over lunch. But let's thank Trevor and Josiah.
The University of Huddersfield, inspiring tomorrow's professionals.